Good morning, my dear students. Welcome back to our semiconductor devices course. Now we are in the next or in the second part in our metal oxide semiconductor field effect transistor, or what's famously abbreviated by MOSFET lecture. Let's now start our lecture. Okay. First, let's now review the first part in the lecture where we were interested in the academic week number 8, if you remember. Now we will start in academic week number 9, and we will start in the second part of the MOSFET lecture. In the first part of the MOSFET lecture, we were interested in the part where we study how current will move from the drain to the source, or we can say how electrons will move from the source to the drain. Here is a schematic diagram of a MOSFET. We have a gate oxide, a gate metal, a B substrate material. We have a source and drain both with an N-type semiconductor material. We have a metal here where we have a contact for the source and the contact for the drain, and we have a fourth contact with the body. As I told you, most of the time the body will be connected to the source. Now we start to plot the energy band diagram for this cross-sectional area. Here you have the N-type, here you have N-type, and in between you have a P-type. This P-N junction construct a barrier for our structure. So electrons will not be able to move from the source to the drain, or from the drain to the source due to this intermediate barrier. So in order to have a current flowing from the source to the drain, or from the drain to the source, we should have an electron. So we should somehow get rid from this building potential in between the source and the drain. We first start by putting a positive voltage to the gate. This positive voltage will accumulate electrons here. Of course, the substrate is a p-type. However, it still includes a minor value of electrons. So this minority carrier will now be attracted to the surface and will construct a bridge between the source and drain. This bridge is an N-type bridge. So now we have what's called channel. Accordingly, we define what's called the threshold voltage, which is the voltage needed on the gate in order to construct the channel between the source and drain. Now let's come to the second question. Why electrons in the source should move to the drain? What motivates electrons in the source to move to the drain? In order to create such a motivation, we now add a positive voltage on the drain. So now electrons is positively attracted to the drain. So electrons will start to move from the source to the drain, and basically the current will be from the drain to the source, which is the reverse of the direction of that. As you can see here, by increasing the voltage on the drain, more electrons will be attracted from the source to the drain, and more current will flow. So we have the relations that the current and voltage here are linear. I mean the current flowing from the source to the drain, or basically from the drain to the source, and the voltage applied to the drain. They are now linear. As much voltage as you put, as much electrons move from the source to the drain. However, now we start to study the probability of finding an electron in the channel, and we basically make a very simple example. We say that if you put an attraction source here, for example, a magnet, and if you put a piece of iron here and a piece of iron there, now the probability for this piece of iron in the right-hand side of the channel to be attracted by the magnet is much higher than the probability for this magnet on the left-hand side of the channel to be attracted. So here the probability to find an electron is low. Here the probability to find an electron is high, because here you are so near, you are so close to the attraction force, so electron can easily attracted. Here you are a bit far, so the probability of attraction is less. That's why we can plot that channel in this form. Here fewer number of electrons exist because the probability to find an electron is lower. Here higher number of electrons exist because the probability to attract an electron is lower. So this is the shape of the channel. This ramp represents the probability to find an electron, because if you remember, this channel or this gray area is created due to the attraction of the electron by the voltage of the gate. Now, what if we start to increase this VDS more and more? We reach what we call the pinch off. The pinch off is the voltage at the drain at which the probability to find an electron in the drain channel interface is equal to 0. This channel becomes now with a 0 width here. That's why we call this a pinch-off point. Basically, this pinch-off voltage is called the VD SAT and is equal to VGS minus V threshold, as you can see here. What if we increase the voltage above VDS? Now the pinch-off point will start to move toward left. As you can see, this area becomes with 0 electrons, with 0 holes. So this area is now a depleted area. Electron will move from the source till this point, and due to the very high attraction force by the drain, electron will tunnel this depletion region. However, this somehow increases the resistance of the channel because this area is a depleted region, which is basically an insulator. So the resistance here is a bit high with respect to the resistance in the channel. This is the whole story. We start first with no channel, P substrate, then we add positive voltage in order to create a channel. This channel will take this ramp format and we will have a pinch-off when VDS equal to VGS minus V threshold. Then the pinch-off will start to go toward the left direction to the source. Now, this is the ideal IV curve. As you can see, we have 3 regions of operation. The first region of operation when VGS is smaller than V threshold, so we don't have current the cutoff region. When VGS is greater than V threshold, then you have a linear relation between the ID and the VDS at different VGS, as you can see. When VDS starts to be greater than VGS minus V threshold, then we have what's called the saturation region. This is the 3 region of operation for a MOSFET, but this is basically what we can call the ideal curve. There is another, we can say that this is the real IV curve, where here there is an internal resistance in the saturation region due to the depletion region, as you can see here. Here the infinity is the resistance is infinity, and here we have a finite value of the resistance in the saturation region, and the current is no longer saturated. Actually, it starts to increase, but with a difference too by increasing the VDS. This was what we studied in the previous lecture. This was the part 1 in our lecture. Now let's do the second part in our lecture. In the first part, or in the first slide, actually in this lecture, we were interested to plot the energy band diagram across this cross-sectional area, across the N, B, N. This energy band diagram was important in order to study or in order to understand how electron will move from the source energy band diagram, or from the source well to the doping well. So we start to plot the energy band diagram in this junction, which is an NBN junction, and then we start to study different voltage effect either on the gate or on the drain in order to make current move from the source to the drain. Now we will be interested in another type of an energy band diagram, which is somehow a vertical energy band diagram. What if we study this energy band diagram? Here you have a metal, here you have a semiconductor, and here you have a metal, insulator, and a semiconductor. So now we are interested in a metal, insulator, semiconductor junction, as you can see. Previously, in the previous chapters, we studied the PN junction, we studied the semiconductor junction. For example, the PN junction. The PN junction was a semiconductor junction. Actually, what we studied in the part 1, which is NBN, is another form of a semiconductor junction. In the next chapter, we will study the bipolar junction transistor, and also it's a semiconductor junction. In the previous chapter, chapter number 4, we studied what we call the metal semiconductor junction, either in a Shockley diode format or in an ohmic format. Now, we will study a third type, which is a metal oxide semiconductor junction. Let's now first try to understand how we should construct a metal oxide semiconductor junction. Okay, here is the junction. Let's start with the most famous energy band diagram, the one on the right. This is a very usual energy band diagram for a semiconductor meter. Here you have an EC conduction band, you have an EV, which is the valency band, and you have an EI, which is the intrinsic Fermi level. And as this region is a p-type, we should expect that E Fermi is more closer to the valency band, so we have here EF. You are now, or you should be now, familiar with all these terms. If you remember, we defined in chapter 4 what's called the work function or the affinity level, which is the energy between the EFI or the Fermi level and the last and the most last energy level of the material, which is called the affinity level or the work function level. And we define this by phi S. If you remember here, S stands for semiconductor. We do the same while we were studying the metal oxide junction, if you, or sorry, the metal semiconductor junction. So we do the same terminology. So you should not, if you study lecture number 4, you should be now familiar with this phi S, which is the work function for the semiconductor. Now we have another term which is phi F. Actually, this phi F is not a new term for us because it describes the distance between the EI and EFI. It's already a known distance for us. We can actually calculate it. We know that this phi F could be equal to 0 if the material is intrinsic, because if the material is intrinsic, EFI will go to EI. And now if the material is p times, this phi F will go down, or EFI will go downwards, and you will have this distance. And this distance is basically, it's proportional to the doping. So by increasing the doping, the Fermi level will go closer to the EV, and this phi F will increase. So it's somehow not a new term for our knowledge. Maybe it's the first time to see the phi F, but I think you already know the physical meaning of the phi F. Now, this is what about the semiconductor part on the right-hand side. Let's now turn to the left-hand side where we have the metal. Again, if you remember, we say that for a metal, we don't have a conduction band, we don't have a valency band, we only have a Fermi level. And we define another work function, which is phi M, which represents the work function for the metal as the distance between the affinity level or the work function level and the Fermi level of the metal, which is Q phi M, as you can see here. So this is Q phi M, and this is Q phi S, and as you can see, this is the diagram we are showing. Okay. Now, as the voltage applied here is equal to V equals 0, there is no voltage applied on this MOSFET structure, as you can see here. So we should assume, or we should know that this MOSFET is now under thermodynamic equilibrium. Along our course, we usually agree that the sign for a thermodynamic equilibrium is the alignment of the Fermi level. So as you can see here, the EFS, or the Fermi level of a semiconductor, is aligned with the Fermi level of the metal. So this is the sign for a thermodynamic equilibrium, as you can understand. Please note two very important notes. First, in the oxide region, we don't have either Fermi level, either a conduction band, either a valency band. It's an insulator, or it's a depleted region. No free carrier exists. That's why we just represent this area. So this semiconductor area, this oxide area is a depleted area where there is no energy level exists. We are not interested in any energy level here. So it's just an oxide thickness, as you can see, with nothing inside. The second important note is that here in this example, we have an assumption. This assumption is that the Fermi level, the affinity level of the semiconductor here is aligned with the affinity level of the metal. The working function, or the last metal, the last energy level in the metal is in the same value as the last energy level in the semiconductor. That's why you have this edge as a flat edge. However, in principle, this is not happen everywhere. Sometimes, in some examples, you may see in the final exam, you may see in the sheet, you will find that this energy level is aligned, EFM is aligned with EFS. However, this is not aligned. This is simply because the values or the levels here are not the same. So in principle, when you are seeking for thermodynamic equilibrium, you have to check Fermi levels, not any other level. Maybe by chance, as this case, the affinity level in the semiconductor is aligned by the affinity level in the metal. But this is not a common case everywhere. Now, let's turn to the second point. What if we apply a voltage on the gate? Now we have two possibilities. This voltage may be a positive voltage, which is the voltage needed to create the channel, or maybe a negative voltage. Okay, let's start with the odd case. What if the voltage on the gate is negative? When the voltage on the gate is negative, that means simply that this region in between the source and the drain will be accumulated by holes, not an electron, because simply the negative voltage will attract holes. So this region, which is the channel region, will be a more p-type region. So in order to demonstrate this impact on the energy band diagram, we will have an energy band diagram like that. First of all, no longer thermodynamic equilibrium, as EFM and EFS are not applied. Second, as you know, we can measure the doping by measuring the distance between the EFM and the valency band. So as far as we go here to the border, the material become more p-type, as you can see here, because this is a negative charge. So what will be accumulated here is holes. So the materials will be more p-type by going toward the border here. And as you know also, the energy of the holes decrease upward and increase downward. So holes here, holes in this region will start to go there in this area in order, or because this area has a lower energy. And here you will have accumulation of holes, as we can describe it here. Here you will have an accumulation of holes. So this is an energy band diagram for an n channel MOSFET when a negative voltage is applied to the gate. So what we can call this region, we can call it here, what we can call it is the accumulation region, because in this region we accumulate holes in this border, and this is what we can call a MOS capacitor, because in this case you have holes here, you have negative charge there, and you have a dielectrical material in between. So this is typically a capacitor. Two charging blades, one with the negative, one with the positive charge, one with the negative charge, and oxide layer in between. So this is a typical capacitor. So now we have a capacitance due to this MOSFET, and this capacitance is due to the negative charge. So this is the first stage while dealing with the energy band diagram across the metal oxide semiconductor junction, which is a vertical junction. Now let's turn to the next step. What if we apply a positive voltage to the gate? Now, when you apply the positive voltage to a gate, first, you repel holes from this area and you start to accumulate electrons. This accumulation of electron will turn the doping of this area, which is a channel area, from a p-type material to an n-type material. So let's see here what happened. As you can see in this case, the EFI, or the EFS, sorry, the Fermi level for the semiconductor starts to go far from the valency band. So the material is now the p-type doping is lighter more and more. Now, if I gave you this energy band diagram in the exam and I told you, is the applied voltage in this case is the threshold voltage? Here you have to remember the definition of the threshold voltage. The definition of the threshold voltage is the voltage needed to turn the doping of the channel from a p-type to an n-type. Now, is this point an n-type material? Is an n-type doping? The answer simply is no. It is still a p-type, but with lighter doping with respect to here. Because here, as you can see, EFS is still below EI. So the material in this point is still a p-type material. However, its doping is lighter. Now this V is smaller than the threshold voltage. We have an accumulation of electrons. We are toward to invert the doping, but still not inverted. What if it looks like that? Now the inversion occurs. Now in this point, the EFS is greater than EFI. So in this point now, the material is an N-type, and now you have an inversion, and now we have a threshold voltage. So this QV is equals to or greater than the threshold voltage, and now you have what's called the inversion layer. So we have three regions, or we have three up till now. We have the accumulation, where a negative voltage is applied to the gate and the hose starts to accumulate. We have the depletion, where you get red from the hose, but still you don't have an electron. You get red from the hose, but you don't have an electron. Why I said so? Because in this point, the material is toward to be an intrinsic, but still not N-type material. And finally, when the voltage is greater than this threshold, now you have an inversion, because at this point, the material is N-type, or the material is N-doped. Now, this happens when a positive voltage of the gate greater than this threshold is applied. Here's the overall graph. As you can see, here you can examine that this voltage is enough to make the material as an N-type across the channel, as you can see, because the E Fermi S or EFS is greater than EI, and this is a relation where you can calculate the phi S, or the threshold potential at this point, which is equal to KT over QLN NA over N. Now we have also some other application for this MOSFET. By the way, all these equations are not required for you to memorize. It's just demonstrating equations in order to understand the electrical field, the charge inside the capacitor, inside the MOSFET. And now let's turn to this important graph. This important graph represents the accumulation or the depletion of a charge across the semiconductor. Here you have two axes. This x-axis is the VGS, or the voltage of the gate, and the y-axis is the Q. And here, this is the origin point. This is the point of origin. Okay. At this point, we have VGS is equal to 0, so you don't have a charge. Please remember that this graph, the y-axis here, is in absolute. So both positive and negative charge will be represented in the first quad of this graph. First, let's start with the accumulation phase. When the VGS is negative, this region. When the VGS is negative, what will happen simply is that you will have a huge amount of charge that is accumulated on this region. So here the charge is accumulated in this manner. So we call this area, we call this region as the accumulation region. As you can see here, this charge starts to increase by increasing the voltage applied. So as much as negative voltage you apply on the gate, as much as holes you will attract on the generation. Now, in the positive half cycle, or sorry, in the positive VGS applied, we have two regions. First, we have the depletion region, which represents amount of a charge accumulated, but it's still, the voltage applied is still smaller than VGS. When the voltage applied is still smaller than VGS, the material will repel holes. You don't have still enough electrons to make it in time. It's stored to be intrinsic, and we call this as the depletion region, as you can see here. Until you reach a point where it's called the threshold voltage, when VGS is equal to the threshold voltage. Now we have the inversion layer. Now you have the inversion phase, where electrons starts to accumulate and forming an N-type material, and this electron starts to increase by increasing the voltage applied to the gate, as you can see. So this region actually or this graph actually is divided into three regions. It's an accumulation region when the VGS is negative. It's a depletion region when the VGS is positive but still smaller than V threshold. And here we have the we have the inversion region where the voltage applied is greater than V threshold and they have an accumulation of negative charge. So this is the charge accumulation graph across the MOSFET structure. You can here describe this graph in the three regions needed for the operation of a MOSFET. Now, this is the end of our lecture. We have finalized now what we can call the MOSFET operation. We studied the MOSFET operation from two perspectives. The first perspective was an PNP junction or NPN junction. Accordingly, is it an N-channel MOSFET or a P-channel MOSFET? And we study how the channel is created, how we can, how current will move from the drain to the source, or how electron will move from source to the drain. The condition for that, the region of operation. We plot the ideal and the real IV curve for a MOSFET. After that, we go to the vertical junction, which is the metal oxide semiconductor junction, and we start to study the same principle, which is the creation of the channel, but from this perspective. And we study how we can plot an energy band diagram for a metal oxide semiconductor junction, how we can understand this energy band diagram, how we can check the thermodynamic equilibrium, how we can, or what will be the shape of this energy band diagram when the energy applied in the gate is positive or it's negative, and how the charge will accumulate on the material. These are the different cases we studied in this lecture. Now it's the end of for the MOSFET lecture. In the next lecture, inshallah, we will go to the bipolar junction transistors, where we will spend weeks number 10 and 11 in understanding the bipolar junction transistors. And finally, we will terminate our course with the final lecture about the tunneling field effect transistors. Thank you very much for your concentration and see you in the next lecture, inshallah.